before we talk about, I should have drawn a loaf of bread as a visual. Okay, let's imagine a loaf of bread, right? For our purposes right now, I want to imagine, see, okay, that we have a perfectly rectangular loaf of bread. Okay, so we can't see this back edge as it comes across here. Or a stick of butter, I suppose. That could be a stick of butter as well. Okay, the profile of that on the front edge looks like what shape? The front edge that's facing you. Okay, what does that look like? A rectangle. Okay, the side edges have what profile? A square. Okay, now depending on how you slice it, you will either get a bunch of rectangles or a bunch of squares. So typically, let's say it's a stick of butter. Okay, typically you're going to slice your stick of butter like this. You'll slice off a slab, and you'll slice off a slab. And those sticks of pieces would also have profiles of squares. But you could also slice, if you really wanted to, your butter this way. Okay, and if you decided to slice your butter that way, then what profile would those slices all have? Okay, they would be rectangles because you're slicing it the long way. All right, okay, so I just want you to think about that. Now, this example, all of the edges are perfectly straight. Therefore, the geometry is really easy. And it's easy to find the volume because you just do length times width times height and everything works out great. Okay, but what about if the edges are curved? Okay, it's not as easy to find the volume anymore. All right, so let's think about something that is curved but still perfectly symmetrical. So let's think about an orange. Okay, so, all right, trying to show that it's three-dimensional. Okay. Okay, if I sliced my orange this way, not into wedges, but into slices, what is the profile of every slice of orange that gets cut away? They're all circles, okay? All right, so that's starting with a perfect sphere. What if you start with a potato? Okay, potato more like this. But if you slice your potato, or a cucumber, maybe, okay, and if you slice that, oh, come on. Okay, the profile of each of those slices is also a circle on the outside. Okay, all right, this is the idea behind what we're building up to for the calculus of irregularly shaped objects. We are going to take an irregularly shaped object and we're going to slice it very thin. And the slices are going to have a different profile shape than maybe the original object. But if we can slice this into thin enough slices and add them all up, then we will have volume. Okay, if I could take all these pieces and put them back together, we would now have volume. That's the idea behind it. Okay, so let's start with drawing some shapes that are maybe not quite as regular as what we would think about. All right, so a 2D parabola, let's start with that. We're pretty good at drawing two-dimensional parabolas. Okay, and I would like you to draw the parabola x equals y squared. All right, what direction does that two-dimensional parabola open or face? It faces to the right. All right, so let's draw that in 2 dimensions. That means we have an x-axis, we have a y-axis, and this parabola has 2 branches. It fails the vertical line test, but that's okay. And that is a 2-dimensional parabola. Now the trick is drawing this now, converting it into 3 dimensions. And so what I want you to do now is you keep your x-axis the same, But your y-axis needs to lie down flat, as if you are lying, instead of, straight up and down like this, we are now going to lie it down flat this way. And so the best way to draw that is to kind of go like this. Even maybe more slanted than that. Okay, that's the y-axis. So if we are lying this parabola down flat, we have to think about what it's going to look like now. So let me give you, okay, so you'll have to look at this. This is facing you, okay? Now if you lie it down, how does the perspective of the parabola change? Okay, when you're like this, everything is evenly symmetric, but when you lie it down, the perspective of the parabola changes a little bit. Okay, so when you draw it and lie this parabola down, the two sides of it, one is going to be closer to you than the other, right? And so the one that's closer to you is going to look bigger. And so when you draw it, it's going to look more like this. But then this one's going to look smaller. Okay, let me try and draw that again. Okay, it's still a parabola. It's just your perspective of it looks different because you are now lying one end of it down. And sometimes it will help to make the back of the longer one, the back of the one that's smaller than you, a little bit longer, and maybe even connect the edges in a way that's parallel to the y-axis, and that might help you see it a little bit better. Okay, we know that this parabola is infinite, but if you, something that's parallel to the y-axis. And what we're going to be introducing is the third dimension z-axis, which is coming straight up this way. And then we can't see the bottom side of the z-axis down below. So we've got a plane. The xy plane is now horizontal, and the y-axis is the vertical piece that pierces the plane and comes straight up. It pierces still at the origin. That origin has three coordinates, x0, y0, and z0. We call that 0, 0, 0. It's now a three-dimensional thing. Okay, so we have this parabola lying down. I'm going to shade it like this. It just helps with perspective for you to draw your shades in ways that are parallel to the y-axis. That's still two-dimensional. It's flat. We're going to create a third-dimensional object. On the end of the parabola, where I have my dotted white line, okay, coming up out of that and growing, like rising up from it, is going to be a square. And so coming straight up from the edge of this end of the parabola comes a square. Okay, so the edge of where my parabola stops is a perfect square, which means if I measure the bottom of it, then the sides are the same, and it's all perfectly square in all the dimensions all the way around. Yeah? Which view? Like sideways? If you looked at it straight on sideways, you would see this shape. If you looked straight sideways, the bottom would look flat to you. This would be the edge, and these things would be curving down like that. Yeah, so like a half parabola would be following the parabolic shape down. That's what you would see on the side. So not a true rectangle. I mean a triangle. Okay, that was our first try. Yeah. Okay, so yeah, there's imaginary axes that they use. Yeah, we're not going to get into any imaginary numbers, but I think you're thinking too of like vector graphing that you did, where you had like an y-axis and a j-axis when you were in Ham, and you did like something something I plus something something j, and that was vectors. Yeah, and we do vectors in BC calculus, but we don't do any vectors in our class. But if you take calculus next semester in college, I mean, yeah, if you take it, you'll for sure see that show up again. Okay, let's try it again. That was our first practice. Okay, so I want to try again drawing another shape with the bottom being at the parabola. All right, so give yourself a new space. And let's try again for practice. So this is X, Y, and Z. All right, and draw another parabola in the same way that you did it before. And make the edge of the parabola, like make one edge longer than the other for perspective, and then draw something parallel to the y-axis that'll be your edge. Okay, so that's our second try. We're going to try this again. Okay, this time, instead of having a square grow up, rising up from the base of this parabola base, let's have a semicircle rise up from the edge of the base. All right, so we're going to have a semicircle come up. And again, it has to be a little bit elongated. There we go. I'm going to extend my x-axis a little bit, I think. And then the next slice right behind it would be a slightly smaller semicircle. And the next slice behind that would be a slightly smaller. And each time we work our way back, our semicircles are getting smaller and smaller and smaller all the way back. And so I usually make my profile one on the end a little bit bolder so that I can really, let me just thicken my line here a second. Try that. Okay. So I'm going to make my edge profile one nice and bold. Okay, there we go. And then trace kind of the path of this. All right, there we go. Okay, so again, now if you look at the front profile of this, if you turn it and face it towards you, what shape will you see? A semicircle, right? But still, if you look at the bottom is still going to look like a parabola. Okay, and again, we're going to learn how to find the volume of something with descending semicircles. The semicircles get smaller and smaller and smaller as we go. Okay. All right. You'll get better every time you do it. You'll get better as you go. Okay. So here is the main idea. Whoops. All right. The main idea is that every 3D object can be sliced into two-dimensional sections, pieces. You know what? Let's call them cross sections. All right, so give me a knife and a three-dimensional object, and I can slice it for you. Okay, boom, boom, boom. Like I always wish I could be as fast as those cooking shows where some of those people are going, you know. Oh, I'm really slow when it comes to slicing. But give me a knife and anything that's three-dimensional, and I can slice it for you. Okay, and then I could put the slices back together, and it would look exactly the same. Okay, assuming I didn't lose a slice or something, but I could put it all exactly right back together again. if you slice it thin enough, or thinly, how many cross sections will there be? Okay, there will be infinite cross sections. There we go. I want you to think of them as paper thin. Okay, so not like cutting a cucumber into slices, because if you cut a cucumber into slices, every slice of a cucumber is still three-dimensional. It still has length, it still has width, and it still has depth. Okay, but if I could slice it paper thin, I could get them all, so thin that they would be three-dimensional. They would only have area and not volume. Okay, so if the cross sections are thin enough, which we assume that we could make them thin enough, they will only have area, not volume. All right, if the cross sections are thin enough, they will only have area but not volume. But here's the huge thing you have to walk out of here understanding. I can't spell. Infinite cross-section areas added up together what will that equal? It will equal volume. Okay, that is the big idea. That you can turn area into volume if you have enough area, if you have infinitely many of them. Okay? You like literally it's like I could turn area into volume if I just have enough pieces of area. I'm just going to add them all up. Think about a stack of paper, right? One stack of paper only has area because it's too thin. But if I put 100 of those together, now I have volume because every thin piece contributes to the volume. If I have infinitely many of those, I can do that with any shape I want. So here's how you write that in mathematics. Okay, how do you do area in 2 dimensions? What do you need to know? Okay, base and height. Okay, all right, so here's how we're going to write this. All right, area. To add something in calculus is the Greek symbol sum. If we go from 1 slice to k slices, what would we like k to be? Infinite. All right, so in front of that, we say the limit as k approaches infinity. So if you have area anywhere from 1 to infinite, then that will approach volume, and that is how we write that. Now, how do we turn that into calculus? This whole expression right here can be elegantly written with one symbol. Okay, what symbol did we learn? The integral. So the integral of area, and then we tell what axis we're working on. the integral of area will become volume over any interval starting at an A and ending at a B. But that integral symbol, that one beautiful, elegant symbol, encompasses the idea of sigma, the idea of infinity, and the idea of limit, all in one beautiful symbol. Okay, but that's what it represents. Okay, you find me the area, and I will integrate it and tell you the volume. What's the area of a circle? Very good. What's the antiderivative of the area of a circle? Do the math in your head. Cubed. All right. Do you know what the formula for the volume of a circle is? 4/3. Right? Pi r cubed. Right? That 4 is the constant that comes out of there when you do your plus c and you have your antiderivative or whatever, but it all works. Okay. What's the circumference of a circle? Okay, that's one dimension. What's the antiderivative of the circumference? 2 pi r, antiderivative. Raise the power, divide by, what do you get? You get the area. Okay, so if you start with one-dimensional anything, integrate it, you get area. If you take area, you integrate it, and you could take volume. What if you could integrate volume? What dimension would you be moving into? The fourth dimension. All right? Now we can't, it's really hard for us to understand the fourth dimension because we're three-dimensional creatures. Okay, and we cannot picture a different dimension other than the one that we're physically exposed to. I think God's in the fourth dimension. And that's right. And then you talk about fractal dimensions. Fractals are like dimension 2.7. Okay, something between 2 and 3 dimensions. What does that look like? Okay, then you get into the whole time, space continuum. Anyway, we could digress and go over a whole bunch of different things. All right, so let us actually do some problems with this. So let's start with our first one that had a square profile. All right, square profile, which also is another word of saying cross-section. Parabolic base. X equals y squared. Bounds 0 to 4. Okay, square profile, parabolic base, bounds 0 to 4. Find the volume. Okay, so if you back up, when it says find volume, what does it really mean to find first? Find area. And once you find area, then you can let the calculus handle finding the volume for you. Okay, so I'm going to quick sketch the picture that we had drawn earlier, just so we have something fresh to work with. And I'm only going to look at my edge square. Okay, let me focus on that one for a minute. All right, if I am going from 0 to 4, that means along the x-axis, here is, oops, we got to change my pen back. Here's 0, here's 4. If 0 and 4 are on the x-axis, what are the coordinates of the corners? Okay, not quite. 2. This is a square. This is x equals y squared, not y equals x squared. So this would be 4 something, and this would be 4 something. Yeah? Okay. All right. So this would be 4, 2. This would be 4, negative 2. So how long is the bottom of the square? 4. How tall are the sides of the square? 4. What's the area of the square? 16. Okay. What about the square right behind it? Okay. What about the square right behind it? Okay. Well, what would the x be of the square right behind it? 3.9999999999999. Okay. So it would be 4 minus, or a little bit smaller. Then what would the sides be? Also 4 minus. And so what would the area be? 16 minus, a little bit smaller. Okay, what about the one right behind that? What about the one right behind that? What about the one right behind that? We need to find something that would tell us the area of any of the squares working backwards. So I'd like you to find an arbitrary square right here. All right, let's say that's A. Okay, it's not 0, it's not 4, it's somewhere in the middle. Okay. What are the coordinates of the points that are on the parabola right there? If the outer ones, the ones on the yellow square, were 4, 2, this is going to be A something and A something. A what? What are the coordinates there? Rad A and negative rad A. Okay, if you're not sure about how that is, remember this is the parabola x equals y squared, which is also the parabola y equals plus or minus x. Right, it's the same, that's what that is, so that's where I'm getting plus or minus a from. All right, so how long is the base of the square that connects those 2 points together? 2 rad a. Okay, this base right here, connecting a rad a to a negative rad a, the total length of that is 2 rad a. Well, then what's the height of the square that comes up from that? Also 2 rad a. So then what is the area of that square at an arbitrary point? Okay. All right, so the base is 2 rad a. The height, if it's a square, must also be 2 rad a. And the area is then base times height, which is 4a. And all I asked you to do was find me the area. And if you could find me the area, then I can find the volume using calculus. And so my volume will be set up as follows. The integral of 4 times any position on the x-axis. I'm just going to use x as my variable, which is the same as using a, but it's any position on my x-axis. I say dx to show I'm going on the x-axis, and I'm going to go from 0 to 4 as my bounds. And once you have that, that's the hardest part, is getting that set up. Once you've got that set up, the geometry or the calculus is the easy part. Then you just quick do an antiderivative. Antiderivative will be 2x squared plus c. Go from 0 to 4. Plug in, you get 32 cubic units because we're talking about volume. Right, now you can think about the profile at the edge, but when you form your equation, it has to be from a random one somewhere in between. All right, let's try it with the semicircle one. Like I said, you find me area, I can find you volume. All right, so let's do the same. We're going to do a semicircle profile. Okay, so semicircle cross section. Same parabolic base. X equals y squared. Or if you want to think of it differently, y equals plus or minus rad a. And we'll keep our bounds the same. Bounds 0 to 4. Find the area. Oh, excuse me, find the volume. All right. So again, I'm just going to quick sketch it again so that I can be thinking about what I'm looking for here. So I've got this. Down to here. We're doing semicircles this time. All right. All right, so my ending semicircle, one at the edge of the profile, is still going from 4, 2 and 4, -2. But I don't need to know the whole base to find the area of that. For a semicircle, what do I need to know? I need to know the radius. Okay, so this one on the end, what's its radius? Just 2. So could you find the area knowing the radius? You should. 1/2 pi r squared. So if the radius is 2, then you have pi r squared, which is 4 pi. Half of that is 2 pi. But let's pick an arbitrary circle, semicircle, farther back, that's connecting A rad A to A negative rad A. I just need to know the radius of that one. And so what is the radius of an arbitrary circle a little bit farther back? Okay. So you guys tell me, what is the radius? No, it's the radius only. Okay, think about, what did you say the radius was for the edge profile one? You said it was 2. 2 is in the y position. Okay, so what is the radius of the one that's back a little bit? Okay, it's rad A. So then the area would be 1/2 pi times rad A quantity squared. What does that work out to be? One-half pi A. That is the area. It will work for the yellow one on the edge, but it'll also work for any other semicircle. Okay, so then once you have that, you can set up the volume. So the volume will be the integral of 1/2 pi for any x along the x-axis, going from the bounds of 0 to 4. And then you take the antiderivative of that. I would encourage you to pull out 1/2 pi to the outside before you do your antiderivative. So you'll be looking at 1/2 pi times the antiderivative of 1/2 x squared plus c, going from 0 to 4, and then finishing that out. So that would be 1/2 pi times 8, so 4 pi altogether. All right, last example. Any questions so far? All right, I'm going to change the base on you. Circular base, x squared plus y squared equals 9. Rectangular profile, cross sections. Twice as tall as the width. Okay, how can we picture this? Everybody know what a Pringles can looks like? Okay, you give me a Pringles can and a knife. All right, now I'm not going to turn the Pringles can on its side and slice it, because if I did, what slices would I get? I get circles. I want to keep the Pringles can straight up, but I'm still slicing down this way. If I slice the Pringles can that way, the profile are all going to be rectangles. That's what I'm looking at here. Okay, a circular base. All right, so let me see here. Okay, circular base. What's the how big is my circle all the way around? What's the radius? 3. Okay, if it's x squared plus y squared equals 9. So I've got a radius of 3. So my circular base looks like this. But all of the cross sections are rectangles. That's the biggest one, is in the middle. A rectangle here is going to be a little bit smaller. And every time I work my way out, the rectangles are going to get smaller still. Okay, I just need one rectangle. Pick an arbitrary rectangle. Probably not on the y-axis is a good choice, and not, but somewhere, I'm going to pick this one. Okay, that is going to be my rectangle. All right. I need to know what the coordinates of the rectangle are down there. Okay. All right, remember, this is the formula x squared plus y squared equals 9. It's also the formula plus or minus the square root of 9 minus x squared. Okay, that is the edge, that's the circle on the bottom. Y equals plus or minus. So this coordinate right here at position A would have a y coordinate of positive 9 minus a squared. And the other one down here would have the coordinate of negative rad 9 minus a squared. And so the base length of this rectangle connecting those two arbitrary is going to be one y coordinate minus the other y coordinate. That's how you measure length. Take the larger one minus the smaller one. And so the base of this rectangle is the larger y coordinate, which is 9 minus a squared, minus the smaller y coordinate, which is negative rad 9 minus a squared. So put them together, two negatives make a positive. The base is 2 rad 9 minus a squared. That is the bottom of any rectangle that's with a circle on the bottom. How tall will the rectangle be? Twice that. And so if the base turned out to be 2 rad 9 minus a squared, then the height would be 4 rad 9 minus a squared. And so then what would the area be? If you put all those things together, what is the value of the area? 8 times quantity, 9 minus a squared. Once you have the area, that's the hardest part. Then you can set up an integral, and the calculus can be the volume. So the volume would be 8 rad 9 minus any x squared along the x-axis. And what will the bounds be as I'm measuring this circle? Negative 3 to 3 will be the bounds of the entire circle. Or, how else could you do it? I could, instead of using negative 3, what could I use? 0, and then what would I do? Double it. If I can use 0, I'm always going to use 0. So then I'll pull 16 out to the front. And then I can work on the antiderivative from there. So 16 times the antiderivative, 9x minus 1/3 x cubed plus c, going from 0 to 3. And then you evaluate from that point on. Most of the pictures are drawn for you in your homework. Not all. There are some that you have to draw. But it's all about finding the coordinates, the bottom two coordinates of your shape. figuring out what the bottom two coordinates are, you always subtract the larger one from the smaller one to find the length of your base so that you can use that. Now if I had made this a triangle shape instead of a rectangle, okay, if I had said all of the shapes are triangle, all that does, my base is the same, my height is the same, my area would just have a 1/2 because triangles are half of rectangles, 1/2 base times height. If I had said the height was triple, then I just make sure to triple my height. You can vary this in lots of different ways. All right, so that is your first day diving into three-dimensional objects.